Welcome back. Here we are, Christmas Eve, and to do some videos for you. We got started on this review for the A2PC practice test, and we're going to pick it up where we left off. Last problem we took a look at was number 25, and just as a reminder, I think the best philosophy of approaching this would be to perhaps just watch as I go through one of the odd problems, pause the video, and then go ahead and try the even numbered problem next to that, because they're going to be very, very similar. So here we are at 27, simplify. This is a type of problem that I would just describe as a whole lot of easy. There's a lot of things going on here, and even a number of ways we can approach this, but there's not a single hard thing here. Some of this may be a little bit of review. So I'm going to start inside the parentheses. You actually could take the negative to the fourth, make it positive, take this a to the fourth, make it a to the 16th, b to the 16th, 2 to the fourth, a to the fourth, b to the 12th, a to the 8th, b to the negative 12th. But I'm going to go ahead and simplify inside of here first. Although I am going to go ahead and notice that, hey, eventually this negative is being taken to the fourth. Since we have a negative taken to the fourth, ultimately we're going to have a positive. So I'm going to just take care of that negative, realize we have a positive here. In the numerator, there's not much I can do there right now. I have a to the fourth, b to the fourth. In the denominator, I only have a numeric factor of 2. Excuse me. I've got a times a to the second. That's a times a times a to the third. I've got b to the third times b to the negative third. Two options here. I could put this b to the negative third in the numerator, make it b to the third, which cancels this b to the third, or much like this a to the first, a to the second became a to the third, add the exponents, 1 and 2. I can add these exponents and I get b to the 0th. b to the 0th is 1. So this is just times 1. I can do one more step of simplifying. I have 4 factors of a in the numerator, 3 factors of a in the denominator, so 3 of these can cancel 3 of these, and I'm left with just a single a in the numerator, b to the fourth, on 2. And now I can just say this thing to the fourth would be like a b to the fourth on 2 times a b to the fourth on 2 times a b to the fourth on 2 times a b to the fourth on 2. So I'd end up with 4 a's. 4 groups of 1a is a to the fourth. 4 groups of 4 b's is b to the 16th. And maybe the most common mistake is made right here. It's really tempting to say this is 8, but it's 2 to the fourth. 2 times 2 times 2 times 2, 16. Now, if you should be pausing this, or when you go about doing number 28, notice this 3. Unlike the 4 over here, this 3 is not going to affect the fact that this is a negative. 3 negatives makes a negative. This negative is going to survive. Okay, let's take a look at 29. All right, what a negative exponent does, and I could distribute this negative in and make this sort of like distribute, make this 2 to the negative first, x to the negative first, y to the negative fourth. But anything raised to a negative can just act like an elevator key. This can take this whole 2x, the whole argument in here, 2xy to the fourth, go to the denominator and become 2xy to the fourth to the positive first. Likewise, this x to the negative third could come to the numerator. Here's one thing I want to point out. This negative is not affected by this exponent. And that's not really a big deal because the negative would survive it to the third, but it would be a big deal here. This negative n to the fourth, the only base to 4 is n. This is not negative n times negative n times negative n times negative n. This is the opposite of n times n times n times n. So this negative actually survives. Okay, so I'm going to go ahead and let this negative 1 do its elevator thing. Move 2xy to the fourth to the denominator. That would be to the positive first. This is the only negative factor. It's like there's a sneaky negative 1 out in front of this x. That's the only factor that's negative in here. So the whole fractional answer is going to be negative, just a single negative. This x to the negative third times x to the negative third is x to the 0th. That's a 1. I'm going to put it here. You wouldn't have to. And this y to the second times y to the third is y to the 5th. There's nothing left on top, so of course we put a 1 here, and we get negative 1 on, I've got a 2, I've got an x, and I've got 9 y's. So definitely problems you'd want to practice. Like I said, there's not a single hard thing there. There's just a whole lot of little easy things that happen there. Okay. Factoring. If you see 4 terms and you decide to factor, your option is to group. Sometimes we actually group 3 and 1, but most times we group 2 and 2. I like the fact that these are in decreasing order of powers. So I look at the first 2 terms and I say I can take a 4 out. They both have factors of 4, and they both have at least 2 v's. 4v squared times what is 20v to the third? I need a 5 and I need a v. 4v squared times what is negative 4v squared minus 1. Now the whole key to factoring by grouping is now I have to do whatever I can to try to get this to match that. If I can't do it, and I'm not suggesting I can right now, if I can't do it, then I'm going to have to try to group a different way, or perhaps this isn't factorable. So if I have a 25v and I want to get to 5v, I must have factored out a positive 5. And I see that that works. Now the next step bothers people at times, and I'm going to just do a little prelude to it here. Let's say I had 4v squared times a plus 5 times a, and I said factor that. I think all of you would know, hey, we can take an a out of both terms and get 4v squared plus 5. And that's what I'm going to do here. I'm just going to treat 5v minus 1 as though it was a. And I'm going to factor 5v minus 1 out of this term and this term. So 5v minus 1, all of it, times 4v squared plus 5. And then I just need to check and see, does 4v squared plus 5 factor? I don't have a way of factoring that. I don't have a way of further factoring this, so we would be done. 32 would be much like that. Okay, again, factor the function. If we have 3 terms, and before I say that, let me say this. You should always look and see if there's a constant we can factor out first. Can I factor out an x out of all of these? No, there's no numeric factor I can cancel out of this. Later on 39, you might notice, well, I can factor a 9 out of this, and I can factor a 9 out of this. I can't factor a 9 out of that. I can factor a 3 here, a 3 there, can't factor a 3 there. But you should always look and see, is there a constant we can factor out? For instance, in 32, lots of factors for 24, and it shares some with 16, but 15, 1, 3, 5, and 15, 3, 5, and 15 do not go into 16, so we don't have a constant factor here. We would have to factor by grouping. Okay, now, if you have 4 terms, we said factor by grouping. If you have 3 terms, unless you can factor out a constant, our best approach is it quadratic? And for quadratic, we're used to seeing things like x squared minus 5x plus 4. But this is still quadratic if this exponent is double that and there are no x's left here. So this is quadratic. It might factor into x to the 4th times x to the 4th if there are factors of positive 4 that add up to be negative 5, negative 4, negative 1. And we're in pretty good shape there, but we can continue to factor this. We can factor because we have a perfect square minus a perfect square and a perfect square minus a perfect square. This factors into x squared minus 2 times x squared plus 2, and this factors into x squared minus 1 times x squared plus 1. Those are called conjugate factors. A plus b, a minus b, those are conjugates. Here I have a perfect square minus, but this isn't a perfect square. Here I have a perfect square plus, stop, can't factor that. Here I have a perfect square minus a perfect square though. So x squared minus 2 doesn't further factor, x squared plus 2 doesn't, x plus 1, x minus 1, check it, FOIL it, x squared minus x plus x minus 1, and x squared plus 1. Temptation is to say it's x plus 1 times x plus 1, but if I FOIL that, I do not get this. I get x squared plus an x plus 2x. So this doesn't factor. And we are done at this time. So this is quadratic. X to the 6th, x to the 3rd, no x's. We can perhaps factor this. X to the 8th, x to the 4th, no x's. We can perhaps factor this as a quadratic. We can't factor this as a quadratic, but we might be able to factor it by grouping. So if you haven't paused, highly encourage you to go back through 32 through 36, check the answer key that you were provided. I'm not going to do 35 because I think it's just another good opportunity for you to practice. Thus the C number 31. Okay, factor each completely. Well, we just talked about this rule up here where x to the 4th, a perfect square minus a perfect square, can factor. If you have a binomial and you can't factor out a single factor, like you can't factor out a monomial, our only hope is that it's a perfect square minus a perfect square, and this is. And that factors into 2x plus 3 times 2x minus 3. Okay. Let's take a look at 38 just a little bit here. The first thing we should do when we talked about this one a little bit earlier is check and see, can I factor out a monomial? Well, I could factor a 3 or a 9 from here and here, but I can't factor a 3 or 9 from there. But I can factor out a p, and I get p squared plus 54p plus 80. And here's a real challenge for you. I'm going to suggest there's a very, very good chance this factors as a quadratic. That would be more challenging than any quadratic I would have you factor when you take this, I don't know what to really call it, just kind of a qualifier quiz. Okay, evaluate the function. When I teach functions for the first time, I would write something like this, and I wouldn't even have the student do any math with it. I would just have them tell me exactly this. K is a factory that takes things. See, here's K is a factory. I'm building factory K. And when something gets put in there, it squares it, multiplies it by 4, and subtracts the results. It puts K here and puts it puts X. If X goes into it, it puts X here and it puts X here. So K of negative 2X, it doesn't care, the factory workers don't care what comes in there. Whatever comes in there, they tag it with a squared. And here would be a common mistake. No, they tag not the X with the squared, they tag the thing. It takes this thing, this negative 2X, all of it, and squares it. And then it subtracts 4 times the whole thing, negative 2X. Oh, that's not so bad. I get negative 2 squared, negative 2 times negative 2, 4x squared, minus times plus 4 times 2x, 8x. And yes, you could factor a 4x out of that, but there's no need to. Doesn't ask us to give a factored answer. Okay, we got another one of those to look at. G is a factory that takes things, squares them, multiplies them by 3, and subtracts them. Doesn't take t's. It doesn't care about this t. This could be anything. If it was G of pen, I would get pen squared minus 3 times pen. If it was G of pen and marker, I would get pen and marker squared minus 3 times pen and marker. If it's G of t minus 4, I get t minus 4 squared minus 3 times t minus 4. And we should simplify that. Maybe I should write this out because I think common mistake here would be, oh, well, this is t squared plus 16. Let's see. T minus 4 times t minus 4 minus 3 times t minus 4. So that's t squared. Outsides, I get a minus 4t. Insides, I get a minus 4t minus 8t. And I get a plus 16 minus 3t, and boy, I hope you know what the next thing I need to write is. Before 3 times 4, minus times minus, plus, now 3 times 4, 12. So I'm left with a t squared, minus 8t's, minus 3t's, minus 11t's, and a plus 16 and a plus 12 plus 28. Okay, good time for you to pause and try some of these. Okay, graph each equation. Maybe you don't have experience graphing absolute values, but you do have experience with absolute values. And we know that absolute values can never be negative. So we might expect something interesting to happen about the time that that absolute value, the argument inside of it is 0. So I'm going to create a t-chart over here, and I'm going to take a look at this, and this is what I refer to as the MyVox. That's kind of my own term. Most interesting value of x. The most interesting value of x here is 0, because that's when the absolute value is the smallest it can possibly be. Over here, can you tell me what the MyVox would be? I want the absolute value to be 0. Therefore, the MyVox is 3. 3 is what makes that 0. So if I was to be doing this problem, over here I would start with 0 for x. Over here I would build around 3. Okay, I put in 0. I get out 0. Absolute value 0, 0, negative 0, 0, plus 4, 4. This is from the MyVox, this is the most interesting point. 0, 4. And now I'm going to build around that. Put in 1. I get out 1. It becomes negative 1 afterwards. Negative 1 plus 4, 3. I put in negative 1, something to the left of 0. Negative 1 comes out of absolute value, positive 1. But then I get the opposite, or like negative 1 times it, negative 1 plus 4, and it's 3. I think I see what's going on here. Putting 2 in and putting negative 2 into this absolute value are the same thing. They both come out as positive 2, become negative 2 plus 4, 2. If I put, for instance, 4 and negative 4 in, they come out as positive 4, they become the opposite of, and we get 0. That's probably enough evidence for me to see what's going on here. So we get this upside down V shape. What do you think is going to happen here? Upside down V shape? Try it out. Okay, now we got some inequalities. Hopefully by now we're all well versed on graphing lines, particularly when they're in this form, y equals mx plus b. Hopefully we know we start up at 3. Hopefully we know we want to rise 2, run 1, or fall 2, left 1, fall 2, left 1, fall 2, left 1, fall 2, left 1. The fact that this says I want to be less than means I really can't be on the line, because on the line is where y is equal to 2x plus 3. So I just build this electric fence. I just say you can get right up close to me, but you can't quite touch. And then I know sometimes people will pick a point, like put in 0, 0, and I get 0 for x, 0 for y. 0 is less than 2 times 0, 0 plus 3. 0 is less than 3. Oh, 0 is less than 3, so that satisfies the inequality shade below. Or shade to the right, if you like. Here's what I like. Just by looking at this, I should know I want a shade below. I shouldn't know I want a shade to the right without looking at the graph. This says I want y's. Y's go up and down. This says I want y's that are smaller than the line. Well, if y's are small, that's down. That's beneath. So we would shade beneath the dotted line. Likewise, over here, what do you think? Should we be shading beneath where y's are little or above where y's are big? The other difference is y's allowed to be equal to here. Therefore, we would not have a dotted line. We'd have a solid line. Okay, good time for you to try that one. Check your answer key. Identify the vertex and the axis of symmetry of each. These are going to be parabolas. I believe you've had some experience with those. Excuse me just a moment. To find the vertex of a parabola, there's a number of ways to do it. The easiest way to do it is this. The x coordinate of the vertex is at negative b on 2a, if this is in the form of ax squared plus bx plus c, it's negative b on 2a. Therefore, it is the opposite of 8 all on 2 times a negative 1. That's negative 8 on negative 2. That's 4. So I'm going to build a t-chart around 4. What I'm claiming here is the most interesting value of x is going to be 4. Okay, let's see if we can do this within our head. Now remember, I think I'm going to put the first one down here. So we get negative 4 squared plus 8 times 4 minus 20. I see very, very good senior math students, calculus students make this mistake. They call this 16. And they're like, well, yeah, negative 4 times negative 4 is 16. But this isn't negative 4 times negative 4. I often say exponents are as lazy as you allow them to be. So this 2 only wants to work with the 4. It doesn't extend to the negative unless there were parentheses including the negative. So this is negative 16 plus 32 minus 20. Here's a big hint for you. When you do this, when you use this negative b on 2a, this term will always be half of that term, and it will always be the opposite sign of. So anyway, negative 16 plus 32 is 16. 16 minus 20, negative 4. 4, negative 4. And now I'm just going to build around there. So I'm going to go to the right, 5. Putting in 5, I get, just a little scratch work, I get negative 25 plus 40 minus 20. See, I don't have that relationship here. That only happens at the vertex, where this is half and opposite of that. So this gives me negative 45. I don't know why I put it right here in my way. Negative 45 and 40, negative 5. So at 5, I'm down negative 5. Now, I expect at 3 to be down there as well, because I think this is the vertex. Let's see. Negative 9 and negative 20, negative 29. Put in negative 3 here. Let me do that again. Negative 9, negative 20, negative 29. Put in positive 3 here, and I get 24. 24 minus 29, negative 5. And then I could put in 2. If I put in 2, just kind of ignore this. If I put in 2, what do I get? I'll jot it down here. Negative 4 plus 16 minus 20. That's negative 24. Negative 24 minus 16, negative 8. 2, negative 8, and I would expect 6 to be negative 8 as well. And there is my, you guys know what that is, parabola. Okay. Unfortunately, you'll see 48 is almost exactly the same. Almost exactly the same. It would be kind of interesting if you just take a little look how when you get done graphing 48, how it looks compared to this. I think you might be able to figure out what's going on there. But you will have another parabola or two to practice on. As I mentioned, in fact, after I finish these two, I'm going to take a break and come back and finish the rest. Okay, y is greater than or equal to. So if you're really paying attention on the last page, am I going to have a solid or a dotted curve here? Y is allowed to be equal to, so the curve is going to be good. I will make it solid. Should I shade above or below? I want to shade where y's are greater than or where y's are big. Y's are big up. We're going to shade up. But I'm going to start this one out looking when is x equal to negative b on 2a, or negative 24 on 2 times negative 3. That's negative 24 on negative 6. That is 4 again. So I'm going to build my t-chart around 4. And I put in 4, and let's see what happens here. I get 16 times negative 3, negative 48. 4 times 4 times 24 plus 96. Take a look. Half of that and opposite. minus 44. It makes the arithmetic really easy if you understand that. Negative 48 plus 96 is going to be positive 48. Positive 48 minus 44, 4. So here I am at 4, 4. And then I'm going to put in, because I believe that's the vertex, I'm going to put in 3. Now let's see what we get here. I'll use some scratch paper down below. I get 3 squared 9 times negative 3, negative 27. Plus 3 times 24, 72. Minus 44. That is negative 71 when I combine my negatives, plus 72. Negative 71 plus 72, that's 1. And at 5, I'm here. Okay, I'm going to jump to 2. When I put in 2, same as putting in 6. When I put in 2, I get 4, negative 12, plus 2, 48, minus 44. I get my total negatives, negative 56, plus 48. That's a difference of 8, and it's negative, negative 8. Is that correct? Negative 56. Difference is negative 8. So we got, when I put in 2, did I just put in 2? I already put in 2. Got negative 8. 2, negative 8. Sorry. I would expect 6 to be negative 8 as well. I will tell you, you will learn perhaps a quicker way to sketch these things. It still involves negative b on 2a, but there's a much quicker way once you get the vertex. But for right now, this should suit your needs. Okay, I said I was going to take a break, but I'm going to at least wrap up this page. Yeah, I'm going to wrap up this page and our graphing portion. Sketch the solution to each system of equations. Well, I know, hopefully, if I've been paying attention, I know I'm going to have this line. It's going to be a solid line, and I'm going to shade where the y's are a little below it. This starts at negative 1, goes down 4, right 1. Down 4, right 1, or up 1, 2, 3, 4, left 1. Solid line. And I'm just going to put on the ends of it that I'm shading below. Shading below. Then I have this line. If I've been paying attention, I know it's going to be a dotted line, and I shade where the y's are big above. It starts at 2 up here, silly, and it wants to go down 1, right 1. However, y cannot touch it. I cannot touch it because y has to be below, and I'm shading above that line. So my arrow's here and here. So if I could call this region 1, region 2 up here, region 3, and region 4, which region has 2 arrows pointing to it? Right up there. That's what satisfies. I need numbers that satisfy both of those. So if I put in a point like negative 2, 5, negative 2, 5 would be a solution to both of those inequalities. Okay, I'm going to pause it there, and we'll be back with part 3.